All right, today we have Federico Bonetti tell us about non-invertible symmetries, branes, and holography. Take it away.
Thank you. Thank you very much. Indeed, it's always a pleasure to participate to the Quiver meeting, and in particular to be given the opportunity to tell you something about this work in collaboration with Fabio, Ibu, and Sakura. As indeed was anticipated, symmetries are essentially at the core of this sort of questions that I will be discussing today. And I'd like to start with a very brief reminder. These are probably things that more or less everyone in the audience is quite familiar at this stage, mostly to set up my notation and terminology. One of the most interesting conceptual novelties of the past few years has been about a way of thinking about global symmetries in quantum field theory. And in particular, one of the key realizations has been that the notion of global symmetry essentially corresponds to the notion of having suitable topological operators in your quantum field theory. So just to give you a couple of examples, if we have an ordinary global symmetry, which we can call zero-form symmetry, it acts naturally on local operators. And as it's well known, it's implemented by codimension 1 topological defects. So here for definiteness, I'm in 4D, so this would be this M3 support. And I'll try to always use this notation if I can, where I indicate the support and the dimension of the topological defect, whereas the thing in the bracket is what labels the defect, which in this instance, it's an element of a group, the symmetry group. And since these are topological, we can imagine shrinking M3 and to the point where it's surrounding this local operator, then it disappears. And what is left is the operator acted upon by the symmetry. And moreover, since these are topological, if we are given, say, two of them for simplicity, for instance, as two planes, hyperplanes, we can bring them together. It's a well-defined operation. And in this case, the fusion is simply group-like. We get the defect labeled by the multiplication. And in this point of view, one-form symmetries are an easy generalization. We simply modify slightly dimensions and codimensions. Now we act on lines with surfaces. But once again, the fusion, as you can see, is group-like. And in terms of why it's interesting to think about these generalizations in the first place is that it has been observed, and it's ongoing research, that many notions that we associate with ordinary symmetries and that are very useful in the study of the dynamics of QFTs can indeed be extended in useful and fruitful ways to the realm of generalized symmetries. So for instance, we can, of course, say organize the spectrum of operators, crucially both local and extended. There are anomalies. We can do anomaly matching. There is a notion of spontaneous breaking. In some instances, there is an analog of Goldstone theorem. We can try to apply Landau's paradigm in terms of classifying IR phases, in terms of symmetries that are, say, for instance, broken or unbroken, and many, many other applications. For today's talk, I would like to focus on a specific class of generalized global symmetries, and namely the ones that are not invertible. And one way to say what that means is to refer to the fusion rule. It's a fusion rule that it's not necessarily group-like anymore. So schematically here, as you can see, we have two of these defects with some labels A and B, but after fusion, we might have a sum of them with some suitable coefficients. The fact that these symmetries exist in lower space-time dimension is actually has a long and very rich history. What is more recent and was more surprising is finding them in several examples in 4 dimensions and also higher dimensions. And there has been quite a dramatic development in really a year or so. And while these non-invertible symmetries in 4D might seem a little exotic at first sight, they have been found, in fact, in many familiar examples. For instance, they can appear in pure Yang-Mills theory, even in theories that are very close to the to particle physics, like suitable massless limits of QED or QCD, and they have been shown to have important dynamical implications. For instance, there was some application to the effective pion Lagrangian, just to give you an example. And people already have considered some possible phenomenological applications as well, for instance, in the context of neutrino physics. So there seems to be, in a sense, the tip of the iceberg, and therefore it's quite exciting and it's very interesting to try to learn more about non-invertibles in 4 dimensions. And the other sort of angle that I would like to take for the talk is that it's actually useful to also address this kind of questions within the context of string theory and holography. And let me give you a quick motivation as to why I think this can be a fruitful way of thinking about this problem. On the one hand, we know that within the realm of string theory and holography, we can access some regimes of quantum field theory that would be hard to study otherwise. For instance, strong coupling, or another quite remarkable prediction of string theory is the existence of non-trivial fixed points in 5D and 6D, like superconformal field theories. And we know we can, for instance, consider their reductions, and they give us strongly coupled theories in a variety of dimensions, a very rich web of theories. And so it's very interesting to study the symmetries of these. And another point that I find personally sort of very satisfying is to realize that if we think of QFTs in this more stringy perspective, if you wish, they're usually specified by something like a topology of a string configuration or the flux configuration and geometry of space-time. And all these ingredients, to me, align extremely well with this more modern point of view on global symmetries, which really hinges on the topology and geometry of space-time and of the defects. And more concretely, as I alluded to, one of the key aspects in the world of non-invertible symmetries are fusion rules. And sometimes they are quite tricky to compute purely in field theory. So I think it's a potentially interesting avenue to see whether string theory can tell us something about the fusion. And we will see some preliminary example that indeed string theory knows about some of the fusion rules. And to me, that gives further motivation that it can be interesting to consider non-invertibles as they come out of string theory. And indeed, there already has been some progress in a few specific examples. And today, I would like to focus on this case study. So let's pick a specific model which somehow has a good balance of analytic control and non-trivial features. So I will be discussing for the n equals 1 super Yang-Mills with gauge group SUM. And one of the reasons why this is interesting and feasible is because it admits a holographic description within type IIB string theory. It's not quite as like the most standard application of the ADS CFT dictionary. Indeed, it is not a CFT, but there is still a lot that we can do holographically. And in terms of why it has to do with the non-invertibles, I will, as a real review, among the various global symmetries that this model possesses, there are interesting discrete zero form symmetries and one form symmetries, and they have a mixed anomaly. And that's really the key, because as we will see, once we gauge one of these two, the one form symmetry, on the one hand, as it's customary, that means changing the global form of the gauge group, which is a relatively innocent looking operation. On the other hand, we'll see that turns the zero form symmetry into a non-inverted. And since, therefore, this is a concrete example of what we would like to study, and we have its to-be realization, the question we will try to answer is, how is this emergence of the non-invertible, how does it look like in the holographic description in the stringy picture? And
I have a question.
Sure.
Do you really think you have a holographic description of this theory?
Well, in a sense, indeed, it is not literally the SCFT, and it's more standard incarnation. But there is a...
No, regardless of the question whether it's a conformal theory or not. I'm just asking a simple question. Do you really think you have the holographic description of this theory?
There is a caveat that I think it's related to this question, and that it's also important to have in mind. As we will see, the stringy setup I have in mind is actually describing a duality cascade. Its gauge theory counterpart is not just simply pure super Yang-Mills. And in terms of this could raise potential complications, but in terms of the questions related to global symmetries and anomalies that are going to be the main focus today, even though indeed the gauge theory picture is richer and more complicated than pure super Yang-Mills, it's going to be adequate for our purposes. So I hope this starts to address the question.
What kind of global symmetry do you have in mind?
These ones that are listed here. These are the three main ingredients. We need a discrete zero form, one form, and their mixed anomaly. And I will review in a few minutes precisely what I mean by these. Okay, thank you for the question. Indeed, I would like to sort of like spoiler alert, give a brief summary of what the main results are. There are two sides to this story. We can either look at it more in the terms of supergravity and its long wavelength effective description, or in terms of branes. And they're both interesting in their own right. From the supergravity point of view, we will see that the key ingredients are the topological couplings that we see in the bulk action. The bulk action in general is a supergravity action. It's far from topological, but contains a topological subset. And the claim is that those can be used to learn about the so-called symmetry TFT, which is a gadget that essentially knows about the symmetries and the anomalies. More pragmatically, in terms of finding non-invertibles, we will see that there is a recipe that we can apply that is based on essentially studying this 5D bulk action in Hamiltonian quantization by treating the radial direction of holography as Euclidean time. This goes back to works by Witten and Belov and Moore. And we will see in particular that there is the machinery of Gauss law constraints, which is very standard in Hamiltonian quantization, that it's perfectly suited to extract the sort of information we're after. And in particular, to find the objects in the bulk that correspond to non-invertible symmetry generators, and to see the interplay between the boundary conditions that we have in the bulk and whether the symmetries we have on the boundary are of invertible or non-invertible type. Complementary to this supergravity picture, there is a brane picture. And in this instance, we'll see how we have a proposal for realizing the symmetry generators as D5 branes that are at a fixed position in the radial coordinate. They're parallel to the boundary, and we consider a limit where they approach the boundary. And as we will see, in a very, very natural way, the dynamics of the action that lives on the D5 brane reproduces the QFT construction, and also some aspects both of the fusion as well as of the action of non-invertible symmetry generators. So this is a sort of appetizer of the sorts of things that I will explain in the remainder of the talk. And therefore, before jumping into the stringy and holographic discussion, it's probably a good time to indeed, as you can see from the outline, first review briefly the field theory story, and then we will see what kind of holographic setup what are the main features of the Type IIB realization, and how supergravity in branes can indeed uncover quite non-trivial aspects of non-invertibles. Okay, so as indeed it was already asked, it's good to set the stage and remind ourselves of what kind of symmetries we are actually interested in. In particular, indeed, let's focus on the three main ingredients that we need. The first is a discrete zero-form symmetry. It starts its life as the U1R symmetry, that it's broken by a well-known ABJ anomaly with the gauge SUM. And as customary, when we have an abelian discrete zero-form symmetry, a background gauge field for it can be thought of as a cohomology class. In a sense, it's a discrete version of the familiar connection one form that we would have for a, say, continuous symmetry. So this is the first ingredient. The second ingredient is a one-form symmetry. This is ZM, as in SUM, because this is indeed the center of the gauge group, as it's quite standard. And thus, for instance, we know that the charged objects are precisely the Wilson lines. And the background field for this is simply an object of the same kind, but of degree 2. And finally, as I advertised earlier, these two global symmetries have a mixed Toft anomaly. It's a cubic coupling of the form ABB, or more precisely, Pointragin square of B, but we can think of this as B squared. And here it's written as an object of degree 5 in an auxiliary spacetime that extends the physical W4 where our super Yang-Mills theory lives. Okay, so these are the sort of things we need, and let's now see why combining these elements we get something interesting. Let's start by a simple observation, that is that since we have a zero-form symmetry, it's going to be generated by codimension 1 topological defects. So simply things that live on some M3 submanifold of spacetime. And as in my first slide, when we fuse them together, they just have a fusion that is group-like. So in this parametrization, they're just integers mod 2m, precisely as one would naively expect. But we have seen that there is an ABB anomaly. That means that if we look at one of the D3 defects and we try to do a gauge transformation of B2, the other one, it's not going to be invariant. What is indeed invariant is this combination here, where, as you can see, we are attaching some auxiliary M4 to the locus M3 where the defect lives. And we are dressing that attachment with B squared. So this object combined is completely gauge invariant under background gauge transformations. And it is still a genuine operator that lives in our 4D theory, because this dressing is just by a C number, if you wish. So in other words, we have a vanilla non-invertible symmetry, and there is, if you wish, a Toft anomaly on the defect that implements it, but it's perfectly okay. Now, what happens, however, if we try to gauge the symmetry that is associated to B2, the one-form symmetry? So B2 is now a dynamical object. We have to sum over inequivalent B2s. The path integral is just a sum because it's a discrete field. And as I mentioned, we changed the global form of the gauge group. But now something quite dramatic happens to this defect, D3, because now it's no longer a genuine operator, because as usual, sort of like we used to have an anomaly in a global symmetry, which is harmless, but now it would be an anomaly in a gauge symmetry, which is a pathology. And to cure that, following this paper that first proposed this construction in 4D, we stack the defect with a TQFT. So something topological, so that the topological nature of the defect is preserved, but non-trivial, so that it carries an anomaly which is precisely equal and opposite to the one that we have due to the ABB coupling in the bulk. Which TQFT should we choose? It's not obvious, and indeed the choice is not unique. Nonetheless, in this instance, there is a well-defined notion of a minimal choice, and that is 3D TQFT, which is U1 Chern-Simons at level M. And therefore, the new object we should consider is not quite D as is, but dressed with the minimal theory. And this combination is now completely well defined in the PSU theory, and however, becomes the generator of a non-invertible symmetry. Why is that? Well, one way to detect it, that there is something more interesting going on, is to study the fusion of these new defects curly n with themselves or with their conjugate. One in principle could even do more. For instance, what happens if you fuse n with its conjugate, which is, as written here, it's just the sort of its vanilla piece is just the same object that we had, but with opposite charge. But we also have a topological dressing where essentially we flip the Chern-Simons level, if you wish. And when we fuse two of these together, essentially the D part just cancel out. That's sort of boring. And it's all about the topological dressing. And if one does a more careful analysis, that for reasons of time I'm not presenting here, one discovers that the right-hand side of this fusion is a so-called condensation defect. It's like a sum of lower dimensional defects. So it's a sort of very dramatic deviation from the standard group-like fusion rule in that we do find the sum of different terms on the other side. Another example, which is maybe less dramatic but also interesting, is what happens when we fuse this defect with itself. So in this case, the group-like part just fused in the expected way. It gives something of charge 2, so to say. But the topological dressings come along for the ride, and therefore we have a stacking with a U1 level M times U1 level M. And this is a non-trivial TFT. And for instance, we can be more precise. If M is odd, one can demonstrate that this object factorizes into two minimal theories in a way that only one factor couples to the symmetry that was anomalous, and it becomes the dressing. So we have this N of charge 2, and the other curly A becomes a coefficient. So this is another manifestation of fusion rules in the realm of non-invertible symmetry. In this language I'm using, sometimes the coefficient is not just a number, but it is instead TFT. So these are two examples of the sort of fusion, and we will see that we can reproduce the second fusion in string theory, and we also have some ideas on how the first fusion might be realized. Okay.
Can I ask what's happening if M is even? It's not the same.
Well, in that case, we cannot invoke this theorem because I should mention that the minimal theory is defined where its two arguments are coprime.
M and 2 should be coprime again.
So the yes, sort of like what fails is our ability to perform this factorization into the well-defined minimal theory and something else. But we can still think of the right-hand side of the fusion as the vanilla D2 defect dressed with a non-trivial TFT.
So what is AM2? Is it the U2 is level M?
No, it's a bit more subtle. I think it's defined abstractly in that any a theorem states that if there is a given one-form symmetry and a given B-squared anomaly, the TFT always, the TFT factorizes into a part that carries that symmetry and that anomaly, and something else that is sort of completely inert under that symmetry action. But in order to though have this factorization result, we need to be able to define the minimal theory, and that is known. People know how to do it when the two labels are coprime. So in general, it's quite hard to analyze this sort of fusion rules, and one of the reasons why it's hard is precisely that the algebra, if you wish, of these topological dressings can be quite complicated.
So there is no easy independent definition of this A, M, N in general. It's just
no. Sometimes, like precisely AM1s, in a sense, we're lucky. We have a simple
AM1, I understand.
description, and but that's not general.
In general, it's just
in general, it's
something you know exists, and then it appears in these fusion words.
Okay. I think, yes, so that was all I wanted to review from the purely field theory side of the story. And now we can consider the string side. What kind of stringy setup are we looking at? So it's Type IIB, and it's the Klebanov-Strassler setup. So a brief reminder of the sort of ingredients we are dealing with. It's useful to think about it as a sort of two-step process. So first, we can imagine to have just D-branes at the tip of the conical. This would be a conformal field theory. So it would admit a standard ADS5 dual. The internal space is a Sasaki-Einstein, which is T11, the base of the conical. And for this talk, the only thing we need to know about T11 is that topologically it is the same as the product of a 2-sphere and a 3-sphere. And then, though, of course, the more interesting for our purposes, things start to happen when you have fractional branes. So this would be D5s that wrap the S2. They back react, they break conformality, and they give a quite complicated but explicitly known solution in Type IIB supergravity. For what we actually want to do, it's actually enough to consider the large radius regime of this solution, so the so-called Klebanov-Strassler solution. And I'm not giving the full expression because it's a bit complicated. Just a couple of remarks. Indeed, since the field theory is not conformal, we no longer have an ADS5, but there is still a notion of a radial coordinate in this holographic stance. And two key ingredients that it's useful to keep in mind, they will pop up a bit later, are these two facts: that there is a flux for F3 given by the M that measures the number of fractional branes, and that there is a non-trivial B2 on the 2-sphere. There is also a non-trivial F5. I'm not writing down everything, but these two ingredients will reappear. As I briefly alluded to earlier, what's happening on the gauge theory side is actually quite a very rich story. There is a Quiver gauge theory, and with two SU gauge groups, and as it was indeed explained in full detail in the work of Klebanov and Strassler, as we flow towards the IR, we find a duality cascading that one of the two gauge groups becomes strongly coupled, and it's best analyzed if we do cyber duality. That is going to change the ranks alternatively on each node, one node and then the other, and so on and so forth. And if the ratio of n and m is an integer, what one expects at the end is pure super Young-Mills. But indeed, it's not a holographic dual of pure super Young-Mills sort of on the nodes. However, you can be at your favorite step in the cascade, and the three ingredients that are really crucial for us, the zero-form symmetry, the one-form symmetry, and the mixed anomaly, they're all visible. So that's why this construction works well for what we would like to do. Okay, so essentially, those are the.
Now I'm confused. If you talk about a field theory, which is this discussion over here, why don't you just make the previous discussion on this theory and not on super Young-Mills?
Yes, no, that could be a possible approach, I guess. Well, from the field theory point of view, there is a sort of it's more economic, and purely field theoretical analysis is more economic in pure superunions. In terms of the duality cascade, it's something that I don't think, unfortunately, I'll have the time to cover today, but one can also consider, was also considering in this paper here, and the second one at the bottom, what happens in the deep IR, and there we find indeed the not quite the Klebanov-Strassler, but the full Klebanov-Strassler solution, and there are features of that geometry that do correspond to pure superunion. So in that sense, that
you're mixing here the two languages. There is a field theory, right? You started by just talking about field theory. So why can't it just be analyzed just the field theory? No talking about solutions, holography, just the field theory analysis, and then compare to whatever you want, the solution of Klebanov-Strassler, Type IIB. One should have a clear distinction between the two.
No, that's right. It's just that at the level of the field theory analysis, in terms of finding the non-invertible symmetries and seeing how they behave, we don't need a lot of details about the theory. Essentially, these three ingredients are all we need. So indeed, we could apply it in several examples. But the goal of this project was to uncover the stringy origin of those features. So I completely agree that the field theory analysis is completely, so that it stands on its own, and it can be performed in several situations without the need of any other considerations. We were looking at this case in Type IIB in order to see what is the stringy counterpart of those features, because the hope would be then, for instance, to learn something that one can apply to other situations.
Okay, thank you.
Thank you. Okay. Okay, so now we can see sort of like something I have advertised already a few times, and now we can see it in practice. How is this going to happen? So the question is, how can we see the emergence of non-invertible symmetries in the Type IIB description of what's going on? And in order to address this question, we can start from some general remarks that actually apply to other situations as well. And namely, it's a general, generally speaking, we know that if we consider the topological couplings that we have in the holographic bulk action, they are going to encode symmetry data and anomalies about the dual theory. So by symmetry data here, I'm referring to something that can be, for instance, a choice of global structure, such as the choice of the global form of the gauge group. So precisely, say, SU against PSU, which is the same as, which is in the same sort of ideas as, say, changing the spectrum of extended operators without changing the spectrum of local operators. And then anomalies in the usual sense, soft anomalies, non-global symmetry. So we would like to characterize all of this in holography, and our strategy will be to analyze the bulk action, and in particular the topological couplings that it contains. So this is a discussion in holography, but it resonates very nicely with a purely field theoretical concept, that is the one of symmetry topological field theory. In this purely field theoretical notion, the idea is that if you want to study a given theory, it's convenient to think about it as a slab. So this would be this sort of light blue region here. We expand it in one auxiliary dimension with the idea that we can always recover it by shrinking down the slab if we want. The point of this splitting, if you wish, is that symmetries and anomalies are then captured by the topological side. So this would be this green gapped interface in the picture. Interface with the so-called anomaly theory. This is another auxiliary theory that lives in one dimension higher and that contains the soft anomalies. So while these two pictures a priori are distinct, in that the SymTFT is not the same as holography, what our results indicate is that there is a non-trivial interplay between these notions. And in particular, if you're interested in trying to uncover what the SymTFT of your holographic QFT is, one strategy to do so is to analyze the topological couplings in the bulk duo. So that's what we will do, and that's the precisely the sort of inroads that we have into this sort of questions. And let's before jumping to the case that we want to study, let's consider a simpler example, namely AdS5 times S5. In this case, if we look at the bulk action in 5 dimensions, we find this famous mixed BF coupling between the two forms. These are the B2 and C2 in 10D, just reduced on the 5 sphere. And as it was pointed out already in the late 90s and then elaborated upon in several works, it is a choice of topological boundary conditions for this topological term that encodes the choices of global structure, so line operators of the 4D theory. So that, for instance, if we choose the Dirichlet boundary conditions for B2, letting C2 freely varying, we are realizing the SU gauge group. That has an electric one-form symmetry. The charged objects under that are Wilson lines. And if we want to realize them holographically, we can use fundamental strings that, as you can see, are along the radial direction and then touch, so to say, the holographic boundary and give us a non-topological Wilson line. So these are the charged objects, need not be topological. And then, of course, there is the S-dual picture where we exchange B2 and C2 and Wilson lines and top lines. So in a sense, what we would like to achieve is a similar description of what's going on for the Klebanov-Strassler, which, as you can anticipate, is going to involve more moving pieces and it's going to be a bit more complicated. However, there is a clear strategy that one can apply. So first we find the topological couplings, and then we will see that doing a Hamiltonian analysis based on Gauss law constraints gives us a very sort of algorithmic approach to identifying the symmetry generators. So let's look at the first step. What are the topological couplings? Their derivation, they can be derived in various ways. There is a very nice consistent truncation that was worked out for this specific example that contains all the couplings we need, among many others. One can also compute those directly using inflow methods based, for instance, on the methods that I have developed with my collaborators. At the end, though, let me, for the sake of time, just give you the final result. What are the relevant terms we need, and are these 3 terms given here? All these fields here live in 5D, and though they have an origin in 10 dimensions, which is indicated here for completeness, and I have highlighted the third one, the origin of the 3-form C3, because it will appear later. It's the sort of the most interesting one for my purposes today. The other ones, in case you're interested, I can tell you more about where they come from and sort of what the origin of these couplings is. At the sort of like, what are the salient features that we see in these couplings? Well, for instance, the first 2 are BF couplings, very similar to the ones we have seen in the AdS5 times S5 example. And indeed, what we observe is that a combination of BF couplings and Stuckelberg couplings is what's responsible for turning the continuous field of supergravity into discrete fields. So this is, if you wish, how supergravity knows that we are dealing with discrete global symmetries as opposed to continuous ones. And as it's sort of kind of clear, but I'd like to emphasize, this cubic coupling that involves A and this 2-form G2, this is the supergravity avatar of the field theory anomaly ABB. Sorry. And finally, let me stress that indeed the bulk action in its full, the whole couplings, it's far from being topological. In particular, there are, for instance, kinetic terms for all these p-forms, but those are subleading at large radius, following the logic, say, that was already indicated by Witten in his AS5 times his 5 paper. We will adopt the same perspective. Okay, so this is our starting point. And what I would like now to do is to do a holographic analysis. This is all quite standard. We just have to select the holographic radial direction as Euclidean time, and then split our fields accordingly. For instance, this is what happens to a one form, whether it has a lag or not in the time direction. This is all quite standard. And as it is usual in gauge theories, the temporal components don't have canonically associated momenta. They don't enter with time derivatives. Rather, they can be thought of as Lagrange multipliers that implement the Gauss law constraints. So essentially here, by definition, Gauss law constraints, I mean what is imposed by varying the temporal components of our p-form fields. And in terms of why do they have to do with symmetries, is just because they generate gauge transformations. And this is a very well-known point, but I would like to sort of illustrate it with a simple example, namely just for the Maxwell theory. Indeed, of course, we know the action very well, and we know that the momentum that it's conjugate to the spatial part of the vector potential is just the electric field. And in this case, the Gauss law constraint, in this more abstract sense, it's literally the familiar Gauss law from electrodynamics. And why does it generate gauge transformations? One way to see it is to make use of the canonical Poisson bracket that we have in the Hamiltonian formalism, and consider a functional like this f. As you can see, we are integrating the Gauss law constraint on space. And we can see that that's effectively generating a shift of A by a gradient, so a small gauge transformation. This is a very sort of simple and well-known example, but the philosophy, the lesson, if you wish, carries through. Even in our more complicated setup, the same qualitative features persist. So all we have to identify, therefore, are the Gauss law constraints and integrate them on suitable loci in a space slice. What happens if we do it in our example? So here is the topological action, those terms that we need. Let's focus on A1 and its temporal component. The Gauss law turns out to be this 4 form here that we see, this sum of two terms, the exact piece and the g squared. And everything now lives on a slice. So we are sort of like inside a 4D ambient space. We could consider, for instance, a solid ball or some other domain M4 that has some boundary and integrate the Gauss law constraint there. And here in the first term, since it's exact, it's convenient to use Stokes' theorem and write it as an integral of C3. So there's like a holonomy, but the other term survives as an integral in 4 dimensions. And now that we have this object, the question is what happens in the limit where its location, this fixed radial location, goes towards the holographic boundary. Even though in general there are contributions from the kinetic terms, those are going to be suppressed. And therefore, all we need are these two terms that are topological. And the fate ultimately of this object hinges on what boundary conditions we have for these fields. And a choice of boundary condition corresponds to a choice of global structure in our holographic theory. So instead of trying to sort of do a complete catalog of what are the possible boundary conditions, let's consider two examples that are illustrative of the analysis. So the first case is where we let C3 fluctuate on the boundary, Neumann, if you wish, but we keep G2 fixed. If G2 is fixed, there is nothing wrong in dividing by 1/2m and sort of factorizing this object and writing it in this way. And this is nothing but the holonomy of C3 there is a well-defined operator dressed with a C number, which is this G squared contribution. And this might sort of ring a bell. This is precisely the analog of the defect that we had in one of the first slides that was just dressed with this top anomaly, the sort of Pointryagin B term. This is the same. This is still a genuine operator in 3D that happens to have a top anomaly. So in other words, it means we're discussing the case of the SU theory, where we have a vanilla invertible zero-form symmetry. But now we sort of see what happens instead if we choose other boundary conditions, and if we sum over G2 squared, G2. In this case, we have two problems. We cannot just divide by 1/2m. And also we have to, as you can see, this object was written in terms of this M4, whereas we would like something that only lives on the 3D support M3. So in order to resolve these issues, we are forced to do something more complicated than the previous case. And in particular, we have to introduce this auxiliary field, A1. This is a new gauge field. It only lives on M3. It was not part of the theory before. However, it is needed because it gives us this topological action. And now if we formally integrate out A1, we reproduce the G squared coupling, except that if we do it this way, everything has the correct quantization for in terms of transience level. So this is a completely well-defined object for any M3, no matter what the topology. All of this is the counterpart of the PSU case in field theory, where we have seen there was a dressing. And here I'm using the minimal U1 to the U1M dressing, just like in field theory. So that's essentially what we see in supergravity. But one might wonder, for instance, what is the origin of this localized gauge field? Can we understand that part better? And in that regard, the D-brane picture, I think it's really interesting in that it sheds light on that. So let's now switch gears. And the idea now is trying to, instead of using the low energy description of supergravity, use the full power of string theory and all the various objects we have in 10 dimensions. In order to get some guidance of what kind of objects we should consider, however, the Gauss law analysis is very useful, because ultimately what it's telling us is that we should consider objects that have to do with the holonomy of this C3 field. But what was C3 in the first place? That was sort of the highlighted item in the list of 10D origins. That guy comes from the 6th form on the 3 sphere. And this gives us a natural proposal if we think in terms of D-branes. And namely that we should consider a D5 that couples electrically to C6 and wrap it on the 3 sphere so that it has 3 directions outside. There's going to be the support of our symmetry defect. So in particular, it does not extend along the radial direction. Rather, it sits at some fixed value. And we're interested in the limit where this value is large. So we're going towards the holographic boundary. So we have, of course, to check whether this idea is consistent with some basic properties of D-branes. The very first check is what happens to the action. And we know that if we take a single D5, we can describe it in terms of the dBi, and that's the mean topological coupling. Now, since we are at a fixed and large radius, the effective tension of the dBi action is very large, and that effectively freezes out all the non-topological couplings that we have there. All that survives, therefore, are the topological terms, and they take this well-known form. There is this formal sum over all the Ramond potentials, and then the B2, and crucially, here we see the appearance of the U1 gauge field that lives on the D-brane. So clearly, this is not a bulk field; it's localized on the D5 word volume. So the question is whether we can use these couplings to make sense of the physics that we saw through the Gauss law constraint picture. And indeed, we can. In fact, if we take the Westermino action and do a reduction on the free sphere, we precisely reproduce an action of this form. So we see that we start with C3, as it was expected, of course, and we get, in completely sort of natural way, precisely the U1 level M Chern-Simons theory in terms of the gauge field that lives on the brane. So as we can see, this A1, which in the field theory analysis, if you wish, has to be put in by hand in order to construct the non-invertible defects, in string theory has a natural interpretation in terms of the gauge field on the brane. And we don't have to go through the whole computation, but here at the bottom, I'm just sort of flashing real quick how one can see that this is plausible. Namely, if you expand the topological terms, some of them will look like this dA1 squared with C2, and then it's essentially just a game of integration by parts, and recalling that there was a flux of m units of F3 on the 3 sphere, and that is the origin of this term. And now we can repeat a similar analysis. So we have this object that lives at some value of the radial coordinate, and we would like to understand essentially what happens when it gets closer and closer to the boundary. Now, in terms of A1, that is the dynamical gauge field on the brane. We cannot choose what to do with it. We always have to do a path integral over it. In terms of C3 and B1, instead, those are bulk fields. They are pullback of bulk fields. So what happens to them depends on our choice of boundary conditions. So that gives us a freedom of considering several options. And again, I will not attempt a full classification, but rather consider 2 examples. In the first case, we let these bulk fields have both Neumann boundary conditions. So in particular, it means that now it's a game of 2 different dynamical U1 gauge fields. So it's again a Chern-Simons theory, but it has a non-trivial matrix of levels. It's not just one. And in particular, due to this ones of diagonal, this is actually a sort of Dijkgraaf-Whitney type theory with trivial gauge group. So it means that ultimately the dressing of C3 is trivial, and therefore we are describing something invertible on the field theory side. And as you can presumably maybe anticipate, in the other case, I will not sum over B1. So that's like a background. So there is, in terms of dynamical gauge field, there is a single level, M. So we do have a non-trivial topological dressing. It is precisely the same as in the minimal choice in field theory, and therefore corresponds to the non-invertible that we have in the PSU case. And finally, I would like to highlight 2 other aspects of the brane construction that fit very nicely with the field theory analysis. The first is fusion. So we know what to expect in field theory. What do we get on the string side? Well, what we have to do is to consider now a stack of 2 D5s wrapped on the S3. A naive expectation would be that we have some sort of non-abelian Chern-Simons word volume theory. But that would be complicated because that would not fit well with the field theory expectation, which is all a game of abelian TFT dressings. The resolution of this tension lies in the Myers effect. Namely, since we have a B2 gauge field on the 2 sphere, what happens is that the 2 D5 branes puff up, or alternatively, they can be described in terms of a single D7 that now wraps the entire internal space, and though carries 2 units of Ward volume flux. So this is how essentially the new brane knows that there used to be a stack of 2 D5s. In the interest of time, maybe I'll skip this reminder on how this goes on the Myers effect, but in case you're interested, I'll be happy to revisit it. And let's see why it solves our puzzle. So now we have to consider, instead of 2 D5s, a single D7 but we have to account for a flux, a word volume flux. And if one does the computation, the topological dressing is different. And in particular, it takes this form. So now the level used to be m, now it's 2m. And there is also a factor of 2 here in the coupling with the bulk B1. And all these features are perfectly in agreement with what happens on the field theory side. By that I mean, on the field theory side, we have these two U1s. So A and A prime, they couple to the same bulk. And with a series of very simple field redefinitions, we can see a compatibility between these two pictures. So that's quite rewarding. It means that the Myers effect is really at the heart of the fusion on the string theory side. And finally, the other interesting point, link between the brane dynamics and what happens in the field theory has to do with how the non-invertible symmetry defect acts on some operators in the theory. In particular, one can demonstrate in the field theory that if you take a 12th loop in the PSU theory and a non-invertible symmetry defect, now the defect is topological, you can move it and you can move it past the 12th loop. What happens is that a surface is generated that connects the two. This is essentially necessary for gauge invariance. Can we see this in string theory? And the answer indeed is affirmative. It's nothing but the Hanani-Witten transition. And indeed, in this presence instance, the 12th line is realized in the bulk in terms of a D3 with a flux. This is a non-topological operator. It extends along the radial direction and pierces through the holographic boundary. Whereas in the bulk, we have our D5s. Those are the ones that become the topological guys. And they link non-trivially with this linking. And naively, as usual in these constructions, one would reach a contradiction if one tries to move one brane past the other, because linking would not be conserved. And the resolution is that there is a new object that it's generated. In this instance, is a fundamental string. So here, I like sort of the brane directions for illustration. And in fact, this is nothing but a T-dual version of the original Hanani-Witten move and set. So in other words, not only the branes have given us the natural dressing we need, but their dynamics through Myers effect and Hanani-Witten transitions account for crucial aspects of the physics of non-invertible defects on the field theory side. So this brings me to my conclusions. In a sense, we have seen that we can address questions about symmetries and anomalies in a systematic way in holography, using this idea of looking at the topological couplings, and once those are extracted, using a Hamiltonian analysis and Gauss law constraints to learn about the symmetry generators. And then in the second part, we have seen that the brane picture is also able to shed light on the physics of non-invertibles. There are many possible directions that one can consider. One thing that is, well, applies to this specific example and presumably others, is the other fusion rule, the defect with its conjugate. As you might have noticed, it's something I mentioned in the field theory, but I didn't give you a stringy picture for that because we're still figuring it out. But it seems indeed that the notion of tachyon condensation between branes and antibranes is the natural explanation for the appearance of the condensation defect in the field theory side. More generally, as I mentioned, like fusion rules can be tricky to compute in field theory, also due to the algebra of these TFT dressings, which can be quite intricate. Can branes give us a different approach that might be useful in some instances? And more generally, since in a sense, we are still learning about non-invertible symmetries, I think it's still very important to try and construct as many controlled examples as possible. So those can be using branes in holography, this can be geometric engineering, and there have been already some very interesting works on the subject in other constructions. And finally, we could also entertain more sort of more speculative but more general questions. For instance, what has appeared to be the case in the past years is that the best language to describe generalized global symmetries is categorical in nature. But on the other hand, the language of categories has already been used very successfully to describe the physics of D-branes in string theory. So that begs the question as to whether the two sides can be reconciled. And at this stage, it's sort of just an idea, but I think it would be a very interesting direction for future research. And with that, I think that, yeah, I'll finish here. Thank you.
All right, let's thank Federico. Questions? Yeah, apparently we're very clear.
So can you tell me what's the physical interpretation of these objects N3?
N3. So yes, those are the topological defects that implement the non-invertible symmetry in field theory. And on the string side, our proposal is to think of them as rapidly. So I'm not sure whether your question was more towards the field theory side.
There is a state operator correspondence?
Well, that's it. Let me put it this way. It's a little tricky in that on the one hand, we're not really dealing with a CFT, and more importantly, more generally, the representation theory of non-invertibles is still being worked out. Being worked out. There are several open questions. So what I have discussed today is essentially how these fuse together, for instance. But since they do not form a group, we know, like, it's natural to ask what does it mean to be in a representation of such a non-invertible symmetry? And I think that's related to also what kind of states might be charged under it.
Yeah, but you're talking about the operation itself. I'm even talking about the object. I should think of it as an operator, because you were mentioning some defect. So you are assuming some type of a defect.
Sorry. Indeed, I should be. I should be a disclaimer. In terms of, I was implicitly working in Euclidean signature, and there essentially we think of insertions of extended objects in correlators, and the distinction between, like, whether or not they extend in the Euclidean time direction is not so important for the sort of things that I was discussing today. But once we think indeed of the physical Lorentzian signature, it's important to keep a distinction in mind as to whether they extend in time or not, because indeed they would either correspond to inserting an operator in an untwisted Hilbert space, or instead considering a different space of states. But I would say that in terms of in the world of non-invertibles, all these questions are still to some extent open, and we don't quite know yet the full rules of the game. But indeed, it's an extremely interesting area of research.
Okay, so what, at the moment, for the current state, the best would be to think of this as an two operators, which.
Well, depending on the, well, let's see. In terms of, for instance, exploring the dynamical implications of non-invertible symmetries, in a sense, one can have a more pragmatic approach and sort of put these questions on the side, in that even if we don't fully understand the answers to those questions, we can still draw interesting conclusions on the dynamics or and say trivial RG flow constraints. In terms of instead addressing those questions specifically, my guess is that those are intimately tied to the representation theory of these non-invertible symmetries. So that in turn opens up other questions. They have been addressed. There are some works, ideally, we would like to do both. I guess we would like to be able to think of them as defects or as operators. In that, that's what we can do in the realm of invertible symmetry. But how that is actually done, I think it's fair to say it's still being worked out.
Okay. Thank you.
Thank you.
Hi, Federico. I have a question. So for the K-theory stuff and category of branes, I just wonder if you have already thought about considering a stack of these brane objects, and consider a non-abelian word volume action of this stack of D-branes, and how does that tie into the non-invertible symmetries?
Well, I guess that depends on the specific setup. In a sense, in this example, we have seen that the Myers effect, it's very much linked to the non-abelian nature. And it was really key to sort of make sense of fusion. But this is just one instance. So I completely agree. It would be, I think, very nice to construct more controlled examples to see indeed what happens more generally when several stacked branes are on top of each other. I think indeed, we still have to explore more examples to get an intuition, but it would be quite important to do so.
Thanks.
One more question is regarding this holographic duality. Would you do you see any way to analyze cases where we really have a holographic duality, not that you have some quasi-duality?
Yes. Well, for one example is n equals 4 super Young Mills. It's just that in that instance, the presence of non-invertibles is related to a duality or triality symmetry that involves SL to Z. So while in field theory, the construction is essentially the same, in holographic terms, it's slightly more complicated because the sort of symmetries that play a role there, for instance, are related to SL to Z transformations in type IIB. But this has been worked out. There is also an intuition. There is also something that has been worked out as far as, for instance, ADS 5 times RP5. So in other words, we were focusing on this example because for us it was more convenient to identify these three main ingredients in the language of supergravity. But that's not to say by any means that one cannot repeat something in a more clear ADS CFT correspondence. And also, though, let me also mention, it wasn't just for us it wasn't just about technical convenience. It's also useful to go slightly away from the pure CFT because then the physics of one-point symmetries is more interesting. In a CFT case, essentially the same thing happens all the time, whereas in this setup, one can study confinement against deconfining phases, so that sort of like, it was more interesting from a physical point of view for us.
So there are two in this case where you really have holographic dualities. There are two prototypical cases. One of them is the hexagonal tilings, and the other one is the rectangular tilings. And the N=4 belongs to the hexagonal tiling, so we made a comment there. You say that there are still difficulties even in this case. The second prototypical case will be the conical, but you chose to put fluxes and to discuss those fluxes, whereas the conical itself, where you really have duality, is when there are no fluxes, that you just have the conical theory, two gauge will have the same rank, and you say there you won't have a phenomena like confinement. This is the reason you did not choose. And just a question, right? I mean, what happens for the conical? Is there anything interesting for the conical?
Well, let's see. We were sort of on the hunt for a controlled example that had non-invertibles and a non-conformal nature to highlight the physics of one-form symmetries. But in a sense, indeed, one can consider other approaches. And one could even ask, like, I was interested in the non-invertible story, but the idea we're proposing, namely that D-branes can be the origin of the defects that implement the symmetry, those can also apply to invertible symmetries. So it wasn't our main motivation. So from that point of view, I can totally see how one can now revisit other examples where maybe there are no obvious non-invertibles. But that doesn't mean that those examples are trivial. And also one can repeat a similar analysis to try and identify the branes that might be behind those. So indeed, that's something that we haven't done yet, because we were sort of like, more, our main motivation was to study non-invertible symmetries, but I do think a very similar story should work in many examples, including those that don't have non-invertible symmetries that we know of. And I don't see immediately a non-invertible symmetry in the conifold, but we haven't done the analysis. I think, though, it's legitimate to ask whether branes can be behind topological defects there as well, and it would be interesting to clarify this point.
Thank you.
Thank you.
More questions? So I have one in the holographic setup. I didn't see where do you see the boundary between the symmetry and the anomaly TFT?
Oh, yeah, that's a good question. I don't think it's immediately visible in that, for instance, well, let me mention maybe N=4 superjangules, where there are sort of fewer moving parts. In that case, for example, the work of Belov and Moore shows that if in your analysis you include both kinetic terms and topological terms, then you are effectively describing a UN gauge theory as opposed to an SU. But then the question becomes, how do you decouple the center of mass degree of freedom to recover the interacting theory you're interested in? And in a sense, that loosely speaking, the choice of boundary conditions and therefore of gapped interfaces between SymTFT and anomaly are related there to this decoupling process. And Whereas in geometric engineering, the story seems to be a little different. For instance, that there the choice of global structure is implemented by fluxes at infinity, so that in a sense that gapped interface is almost pushed all the way to infinity. So in that sense, I think it's important to keep in mind the logical distinction between those two sides, the purely theoretical notion and what happens in holography. But there seems to be a very interesting interplay. And the question you asked is, I think, definitely one of the most interesting ones.
Okay, thank you.
So I also have a technical question. So in the expansion of these field strengths like F3, H3, and F5, you are only including the omega 2 in the F3, as I remember. Yeah, so that's like due to some 2 cycle.
Yes, no, I mean, we consider the extent, there are like a 2 cycle and a 3 cycle. And if in the paper we consider the most general expansion, there are some constraints that come from the Bianchi identities that one has to take into account. And also the another complication is the self-duality of F5. So here, today in this presentation, I didn't have a chance to sort of clarify those points, but in the paper, in the appendices, we consider all terms, and indeed, as I said, it's a game of cycles in the term space.
But I was thinking that, so in type 2b, because there are multiple field strengths for these R and NS and sector fields. So in principle, you should be able to write down everything in the expansions, right? You know, every convergence cycle, like cocycles.
That's true.
But so it's like, so the reason is your specific holographic setup or some general constraint like the Bianchi identity and these constraints, so that you reduce the number of terms in the expansion.
Let me think. No, I mean, I completely agree with the philosophy in that all field strengths should be expanded on all cycles. In a sense, well, I think for we focused on our aim was to identify the supergravity fields that correspond to the symmetries we wanted to study. So in that sense, we were not trying to be complete in that we did not attempt to account for all the possible P-form fields. In this instance, though, potentially the good news is this full consistent truncation that has been worked out in the literature, in that presumably that consistent truncation features a very rich set of topological couplings. The ones I have studied today are like a subset of those, the ones that are relevant for the problem at hand. Related to the question you asked, I would imagine that the full result would capture everything. In a sense, therefore, the task is to see whether these other terms that I haven't shown today also have an interpretation in field theory. And we have not attempted a full scan of those yet.
I see. Because in the M3 SIMTFT computations, we are doing also Zachary was doing before, I will be with you. So in M3, it seems that you can just expand out every term in the G4 in principle, and you don't get any extra P-form symmetries.
Well, I guess that depends. I would have to remind myself, but I guess like, well, maybe as an example, it's not quite the same, but if you consider M5 branes and you
Yeah.
play a similar game of expansion, oftentimes you find like axioms. Those would correspond
Right.
in a sense to -1 point symmetries in field
Yeah,
theory.
yes.
And,
Yeah,
and
you
those,
have
I mean,
some.
there are many of those, but
Yeah.
I think it's, yeah, their field theory interpretation is not being completely clarified yet. But to me, that's sort of good news. It means that string theory and holography potentially knows, like, it could have interesting lessons that we could learn from those couplings, because they're definitely there.
Yeah.
And they might have
I see. Yes, thanks.
Thank you.
Do we have more questions? Well, let's thank Federico again. I'll stop the recording.